Welcome to this video all about the kinetics of chemical reactions. So this series of video workshops is designed to help the transition of foundation year and first year students into chemistry focused modules, maybe people who don't have a strong previous background in chemistry. You're going to need around 20 to 30 minutes to complete this video workshop. There are a number of quick practice questions throughout. At these points you should pause the workshop and work through the questions at your own pace. To get the most out of this session, you'll need something to write or draw with and a basic calculator. So the calculator app on your mobile phone or a version of Microsoft Excel is fine. You should note that this video is designed to be watched after the one that I did on energy and thermodynamics because it builds on some of the simple concepts established in that video. So here's what we're going to try and cover. We'll start with defining the term kinetics as relates to the chemical sciences, then go on to explore the numerous different factors which can speed up or slow down a chemical reaction. We'll look at three different classes of reaction, those being zero, first and second order reactions, and the characteristics of experimental data we might see for all of them. We'll introduce rate equations, how they're constructed, how we can manipulate them to calculate useful parameters, and how we can use them to solve problems. And finally, just some brief comments on why a certain term in the rate equation has variable units, which is an unusual thing in chemistry. So kinetics in chemistry refers to the rates at which chemical reactions proceed. It's a very important topic for biology related processes. So for example, when drug molecules enter the human body, one of the key stages they go through, as you might know, is metabolism. So biochemical processes convert them into different molecules, which makes them easier to excrete. And that conversion is itself a chemical reaction. And it happens at a specific rate depending on what the drug is, what the enzyme used is, and the temperature. And it's very important to know what that rate is so that a doctor or a pharmacist can dose a patient correctly. Obviously, the consequences of someone having too low or too high a dose of drug can be pretty severe. To start things simply, we need to think about the factors required for a chemical reaction to occur. So, considering, for example, a drug molecule binding to a cell receptor, you might have been taught to think of this as a kind of lock and key mechanism, as in only specific drug molecules can bind to specific receptors in the cell. Well, for the reaction to happen, of course, the two reactants have to touch, but they also have to touch in what's called the correct orientation, or in plain English, they have to be facing the right way. So if the drug molecule bumps into the receptor with its reactive functional group facing away from the receptor, then nothing's going to happen. It's called an unsuccessful collision. Furthermore, it has to bump into the receptor with enough energy, i.e. quickly enough for the reaction to proceed. So if the reactants are going too slowly, they will just simply bounce off each other rather than unite, and again the collision is unsuccessful. Now the activation energy, which is seen on these example reaction coordinate graphs here, you'll hopefully already have met that term in my thermodynamics video, but the activation energy is the minimum amount of energy required for collisions between reactants to be successful and for the reaction to proceed. And what you are seeing when you observe a chemical reaction proceeding is the rate at which successful collisions are taking place. So these are collisions with the molecules, the chemical species in the right orientation and with enough energy to cause the chemical bonds to break and form. In the chemical and pharmaceutical industries, it can be really important to essentially make reactions go as fast as possible because this allows us to produce useful chemicals quicker and allows us to maximize use of equipment and reactors, which can be very expensive. We can do this in two main ways. Number one, increasing the frequency of collisions, And number 2, lowering the reaction activation energy. There are many, many different ways of doing the former. Let's go through some of them. So one of the obvious things to do is to increase the concentration of an aqueous reactant, or to increase the pressure of a gaseous reactant. If there are more reactant molecules existing within the same space, they will bump into each other more frequently. We can also increase the temperature of the reaction. So if we heat up the system, that means that the liquid, aqueous or gaseous reactants will be moving around faster. The faster they move, the more collisions they will have with the other reactants. It's kind of like the difference between driving a car slowly and carefully or quickly and dangerously. You're going to have more accidents if you do the latter. We can also look at the physical form of solid reactants, and by that I mean whether they come in the form of large particles or small ones. So consider a drug slowly dissolving in a glass of water. If the drug comes in the form of a large tablet, when it goes into the water, most of the active drug molecules are trapped within the bulk of the tablet, so they don't get exposed to the water until the outer layers of the tablet dissolve and allow the molecules access to start solvating the inner layers. But if the drug is a fine powder, then the mass to surface area ratio is much lower. So proportionately more drug molecules are exposed to the water quickly and dissolve quicker. A similar but slightly different concept is whether you are agitating or mixing the reactants. So if our drug is in a powder form, but it's dense and sinks to the bottom of the glass and stays still, like we see on the left, it will dissolve again more slowly because a high proportion of the particles are now touching the bottom of the glass or other particles rather than being in contact with the water. But if we constantly mix or shake the glass, we don't allow that to happen, and all of the particle surfaces are constantly in contact with the water. Now, looking at the other branch of control of reaction kinetics, in terms of lowering the activation energy of the reaction, it's simpler to remember. The only thing you'll be expected to know at first year university level is that using a catalyst lowers the reaction activation energy. So a catalyst, as you may know, is a chemical that is involved in a chemical reaction but not consumed or produced in the reaction, i.e. it doesn't appear in a stoichiometric reaction equation. Again, as you may know, chemical reactions usually don't progress in this nice linear way in the reaction coordinate graph pictured, i.e. we start with reactants. They come together in a high energy transition state and they progress to being products. What actually happens is that they normally go through one or more intermediates. If you're not familiar with these definitions, again, I direct you to the thermodynamics video. What the catalyst does is allow a new lower energy intermediate or intermediates to form, ones with lower activation energy than you would otherwise get. So those are the things that we can do to influence the rate of a reaction, but how then do we quantify and predict the rate of a given reaction? Well, the first step involves working out what the relationships are between the concentrations of reactants and the observed rates. It's worth saying at this point that in the next part of the video we're going to be talking about aqueous or otherwise dissolved chemicals, just because that's the most straightforward way of explaining the concept. So I'll be talking about concentrations extensively going forward. Now, for some reactants, no matter what the concentration of it is, it doesn't change the speed at which the reaction proceeds. So on our graph here, we've got concentration of a reactant, we'll just call it A, which will decrease as it's consumed on our y-axis and time on our x-axis. You can see from the line I've just drawn that the rate of reaction does not change at all over the course of the experiment, i.e. it doesn't matter whether there's a huge amount or a tiny amount of the reactant, the concentration of it decreases at exactly the same rate. So concentration is proportionate to time, directly proportionate to time. So if we were to instead plot concentration versus rate for this reactant, all we would basically see is this. And in these circumstances, we say that the reaction is zero order for that reactant, for reactant A. For other reactions, the speed of reaction is influenced by the amount of reactant present, i.e. the more the concentration of the reactant decreases, the slower the reaction will go. You can see this relationship on the graph here. Now, the rate of reaction here has a very specific relationship with the reactant concentration. It is directly proportionate to it. So concentration is proportionate to rate. This means that if we draw the graph of concentration versus rate this time, we get a linear straight line. And in these circumstances, we say that the reaction is first order for reactant A. For still other reactants, and you can probably see where I'm going with this, the concentration of the reactant is even more influential to rate. So you can see that in the graph here, the speed of reaction slows down much more markedly than the first order reaction previously shown as time progresses. Sometimes the rate of reaction is directly proportionate to the reactant concentration squared. So concentration squared is proportionate to rate. So then if we plot this graph with A squared on the y-axis, again we get the straight line gradient. And in these circumstances, we can say that the reaction is second order for reactant A. Now in the real world, annoyingly, things are not this simple. You do get reactions that are of higher order than 2 with respect to individual reactants, and you do also get reaction orders which are not integers, so not 0, 1, 2, 3, etc. But you won't be dealing with these in your studies anytime soon, if at all. I'm just pointing out that they exist. It's important to make clear that what we've just been talking about are relationships between observed rate and concentrations of individual reactants only. To come up with the actual full rate equation, or rate law as it's sometimes called, we need to actually derive it from those individual relationships. Let's consider a simplified reaction here between 3 different reactants progressing to 2 different products. Now, products don't appear in rate equations, so they aren't particularly relevant in this case. The rate equation looks like this. So we've got rate, sometimes abbreviated as KR, that's lowercase k, is equal to lowercase k on its own times concentration of A to the power of X times the concentration of B to the power of Y times the concentration of C to the power of Z. Now, where did X, Y, and Z come from? I will explain. Starting from the beginning, so the rate is the observed speed of the reaction in units of moles per decimeter cubed per second, or molar per second, depending on what your discipline is. It will depend on your discipline which of those in the way in which the units are referred to, but they both mean the same thing. And as I said, it's sometimes referred to as KR. Note that the unit of time can change. It's sometimes seconds, but it's sometimes minutes and sometimes hours. It depends what is most convenient for the speed the reaction is actually going at. The lowercase k term on its own is called the rate constant, and this term is really a combination of all those other factors influential to reaction rate that we previously talked about, such as likelihood of successful collision, temperature, and activation energy magnitude. It's a term specific to a certain reaction under certain conditions, and it can be worked out provided that you know all of the other terms in the equation by simple rearrangement of that equation. And then the terms in the square brackets are the concentrations of the three reactants, and the superscript terms, the powers of terms, now they refer to what order the reaction has been found to be for that specific reactant. And the overall order of the reaction is found by simply adding up these terms. Now, for example, let's say for this particular reaction we've done some experiments and found that the reaction is 0 order with respect to reagent A, 2nd order with respect to B, and 1st order with respect to C. So let's just substitute the 0, 2 and 1 in, which I've done at the top of the slide. Now pause the video and I've got 2 questions for you to think about. First of all, what is the overall order of the reaction? And second, having derived that, how should we simplify the rate equation as a result of this? So pause the video, have a think, and resume once you've arrived at some answers. So the overall order of the reaction is just 0 plus 2 plus 1, so it's 3rd order overall. Now for the simplification, hopefully you should have worked out that any number to the power of 0 is always 1, and likewise any term multiplied by 1 is just that term. So the concentration of a term can disappear from our equation entirely. And for the C term, any number to the power of 1 is just that number. So this also can be simplified as shown. However, do bear in mind that the power of 1 should still be counted when you're adding the powers together to work out the overall rate of reaction, overall order of reaction rather. So that's the simplified version of the rate equation there. Ki is equal to K multiplied by concentration of B squared multiplied by concentration of C. Moving on, one of the things that I found most difficult to get my head around when I was trying to learn this topic as an undergraduate is the fact that the units for the rate constant change depending on the overall order of the reaction. The reason for this is because the units for observed rate are always moles per decimeter cubed per time unit, or molar per time unit. That is what we observe and measure. That cannot be changed. However, on the right hand side of the rate equation, you can of course have 0, 1 or more concentration terms, which all have units of moles per decimeter cubed. And so the K term has to change to nullify this effect, if you like. If you don't understand what I say over the next few slides, you need to do some reading on what is called dimensional analysis. It's very, very important for scientific disciplines. I'll pop a link to a suitable resource below the video. So starting simply, for 0 order reactions, there are of course no concentration terms in the rate equation because the concentrations of reactants don't influence the rate. So the units for K here are simply the same as for the observed rate, moles per decimeter cubed per second to the minus 1 in this instance. However, if the reaction is 1st order overall, we now introduce a unit of concentration on the right hand side of the equation, and so the units of K change to account for this to just seconds to the minus 1. You can see the dimensional analysis of the right hand side of the equation underneath here. So pause the video if you wish to kind of reassure yourself that the dimensional analysis is correct and makes sense before you carry on. If the reaction is second order overall, we've now got 2 units of concentration on the right hand side now. So the K units have to change again now, this time to moles to the -1 decimeters cubed seconds to the -1. So that again, as per the dimensional analysis, everything is kept balanced. So here's the next question for you. What do you think the rate constant units would need to be in our previous example to account for a reaction that is third order overall? So pause the video, again, have a think and resume when you've arrived at an answer. Well, the answer is moles to the -2 decimeters to the power of 6 seconds to the -1. Again, here's the dimensional analysis of the right hand side of the equation for you to check if you wish. So on this slide, what I've done is I've made just a table of units of K for the different overall orders of reaction for you, just to look at, to make this information hopefully easier to remember and recall. Whether the lecturers on your course generally work in units of moles per decimeter cubed for concentrations or in units of molar. The final thing we're going to talk about is how you would practically go about collecting data in a laboratory to find out the order of a reaction and its rate constant. Now, you can only do this experimentally. You cannot predict these things. You have to run a series of experiments. So returning to our simple rate equation at the top here, hopefully you can see from this that if we do an experiment in which we know the initial concentration of reactant C is, say, 0.02 moles per decimeter cubed, and then we do another experiment in which the concentration of C is 0.04 moles per decimeter cubed, provided we keep all of the other variables constant, our observed rate is going to double, increase by a factor of 2, proportionate to the concentration of C, because of that first order relationship. Now, you can get a calculator out at this time and prove this to yourself mathematically. Whatever numbers you put in for K and whatever numbers you put in for the concentration of B, as long as you keep them constant across the 2 experiments, the observed rate is going to double, increase by a factor of 2. Now, if we're going to do something similar for reactant B, in our first experiment, let's say it's going to be 0.1 moles per decimeter cubed, and then in our second experiment we'll put it at 0.2 moles per decimeter cubed, so we're doubling it. What do you think will happen to the observed rate of reaction between those 2 experiments? So this is your last challenge. Pause the video and have a think what the answer to that is going to be. Well, your answer is the observed rate will increase, the observed initial rate will increase by a factor of 4, or 2 squared, 2 to the power of 2, because it's a second order relationship. So whatever factor we increase the concentration by, again, as long as we keep all other variables constant, the observed rate is going to increase by that factor squared. And of course, with reactant A, which isn't even on this slide, it doesn't matter what we change our starting concentration to. It won't make any difference at all to the rate. A favourite examination question for a number of lecturers at this university is to give you a simple experimental data set and ask you to determine the overall order of a reaction and the value of the rate constant and its units. But now, thanks to watching this video, hopefully you'll be able to do just that. And there are 2 examples of that type of question for you to practice on in the associated question work-through sheet. And that is it. I'll just leave you with a recap of the learning objectives. Thank you very much for watching, and best of luck. Best of luck in your future learning with regard to chemical reaction kinetics.